Welcome to this demonstration of ANSA and Meta version 21 for CFD. In this video we will show you the main new features of the version. You can find more information in a related video as shown in the comments, where you will find an extensive list of all the new features. However, in this video we will focus on the major topics. These include the new size field function that allows you to control the mesh size on the surface and the volume mesh, the leak tool to detect leaks in complicated models, the functionality to remesh volume cavities after making local modifications on the surface, replacing parts and so on, new functions in morphing, improvements in the function rotating interface that is used for rotating wheel simulations, improvements in the setting up of an OpenFOAM case inside ANSA, and we will close with a new CFD toolbar in Meta. Okay, so let's start with the first demonstration, the size field functionality. I will start ANSA. Please ensure that when the launcher pops up, you select the CFD option so that ANSA starts with the default interface for CFD applications. This ensures customization and optimum settings for all mesh parameters, quality criteria, button position, as well as access to further functionality through the user script functions. Let's load the first demo file. So here we will talk about the size field function. This is new functionality in version 21. Up to now in ANSA we could control the mesh size through the size boxes, but now we have more functionality. So let's see how this works. We have an empty geometry, an unmeshed geometry, it's cleaned up, and we have two size boxes as before, and these controlled the mesh size distribution. Now let's see what we can do with the size field function. The size field function is located in the Octree menu through size field. You can create one or more size fields that impose restrictions to the mesh size in various formats. First of all, you need to create a new entity, and this new size field entity contains multiple so-called rules. One rule, as we knew it before, was the size box. So we can say that we want to add some size boxes and specify some mesh criteria. First of all, we need to double click on contents. Here, what we select is size boxes, right? So we will select these two size boxes. The content is updated to 2, and then we double click on parameters and we specify a maximum length on them, let's say 40. For the surface and for the volume. You can specify different values. In this case we'll leave it the same. So this is one rule that imposes a maximum length of 40 millimeters inside these two boxes. I will add another rule, and in this case I will pick a closed surface. Here I need to specify a closed surface, and then I will impose a different maximum length, let's say 20. Now, as a closed surface, I need usually to import some isosurfaces from initial CFD simulations, and I will do this now. I will input an Astran file of an isosurface of total pressure equals 0, and you will see that this isosurface has this shape. Now I can go to size field, edit the size field entity, and in the contents here I need to specify the PID that forms the closed surface. So I will pick this one, put it here, and now my two rules are well defined. Having specified the rules, we need to apply the build function. So the Tanza calculates the size field based on both size boxes and the closed isosurface. Once build is pressed, Tanza gives me a preview in 3 directions. I can have some cutting planes. I will select a Y cutting plane in this case, and I can scroll across Y to see my mesh size distribution, and you can see 20 and 40, right? So we have 20 millimeters inside the isosurface, 40 in the size boxes, and it's free outside of that. Once the size field has been constructed and built, remember it's very important to have status ready built. You can now switch to batch mesh, which is ready here, and I will run, for example, the surface mesh. So batch mesh, which also includes refinement due to curvature, features and proximities, will also consider the size field and will refine the mesh accordingly. Okay, the surface mesh is completed, and you can see now, if I remove visibility of the isosurface, you can see how well the surface mesh has been refined due to the closed isosurface and the size boxes. Right? I can also proceed with the layers and the volume mesh, which will also be affected by the size field. Okay, the mesh is completed. I exit batch mesh. I will use some focus commands to remove visibility. Right. And now I will create a cutting plane in the ZX direction. I will pick a node here, put it in a part, and now I can specify, for example, clip no, and cut not visible but all. This means even the volume mesh, which is not visible at the moment. And there is my cutting plane. You can see again how well the refinement has been imprinted, both from the isosurface and the size boxes. Okay, let's have a look at another case. This is an aerospace case, a small one. So we have a plane, we have a size box, and we also have some 3D curves, which you can see in this magenta color, right? One that comes from the wingtip, one that comes from the exhaust of the jet engine, and one across the wing. So let's examine the size field here. I have already constructed the size field. Let's see what it consists of. So we have, remember, the rules can be a closed surface, it can be a surface offset from selected PIDs, it can be a cylinder, which means a cylinder that follows a curve, a sphere that starts from a point, and the size box as you've seen before. Here we have 3 cylindrical size fields that start from the curves, one from the size box, and a surface offset, a complete offset of that plane. Let's see the parameters of a cylindrical field. This is a bit more advanced. It doesn't contain just a maximum value. It contains a radius of influence, right? So at the start, this radius is 200, and because this is a variable shape, at the end it has a radius of 1000. So it's like a conical shape that follows a curve. Also, the size is variable, it's not constant. It means that it starts with a length at the start of 50 millimeters for both surface and volume mesh, and then it grows in the two directions, radially and axially, with different growth rates to specific maximum values. Let's see the surface offset, which is an offset from this plane. We have an offset value from these PIDs. In addition to specifying an offset, we can also specify a translation vector, which means we can take the original PIDs, offset them by a specific distance, and then sweep along a translation vector. And at the end we can have a different offset value as well. This gives us a very nice refinement of the wake of a shape. So our vector is x direction, our distance is 15,000, and we specify a maximum surface and volume length in that space of 300. We could also specify a variable size as well, like before. So, having specified all these rules, and you can see that the status is ready, which means that I have already pressed build, so all the calculation of the size field has taken place and is stored in the file. I can quickly press visualize, and this will give me an overview of the size field. Again, I can sweep in 3 directions and see how the mesh size will vary, and you can see a radial increase across that cylindrical size field. Let's go to the tip. Also, you can see a nice combination of radial increase of the size and axial as the wingtip develops further downstream. We can examine this in different directions, right? To see how the mesh size distribution will vary. And as I said before, once this size field entity has been defined and built, so it has status ready, all the surface and volume mesh that will follow will respect that. So let's quickly switch to the volume mesh, which is the completed case. And there you have the resulting mesh. So you can see the refinement across the jet plume. You can see the refinement which is sweeping downstream of the plane, which was the offset and sweep from selected PIDs. Let's scroll up and down this cutting plane so that you can see also the refinement at the tip vortex. And the sweep from the shape of the plane downstream by 15,000. Remember, the size field is a tool that is set up in the Octary menu, and it affects the surface mesh, the volume mesh in batch mesh, and also of course the surface wrapping and the extreme volume meshing. So it's one entity that controls size in using many different rules and all the different meshing solutions in ANSYS. Okay, let's move on to our next tool, which is the leak tool. It's located in Mesh, Octary Leak tool. There are many cases where the user has to deal with complex geometrical data, either in NURBS or in STL tessellated format, and they need to ensure that they have a watertight description. it's not always easy to find leaks, and it's even more difficult to close them. In this case, for example, we have an STL model where we have quite some large gaps here, we have openings here, and we even have some large missing parts here. So let's see what we can do with our tool, the leak tool. First of all, we need to specify some points where we don't want the fluid to enter. So, as this is an external aerodynamics case, we will specify some points inside the car where we don't want the fluid to leak. We can specify one or more points. Actually, it's suggested that we specify more than one point, as this assists the algorithm in closing the leaks. So in this case, I will specify 3 points. I can type the X, Y, Z coordinates, or I can click on the arrow button here and pick a position. So this is one position on one window. I pick a second on the opposite side, and then ANSA finds the center of the 2 points. So this is 1 point. Then I will do the same for the rear part of the car. Again, a center point there, and 1 there. Okay, so we have 1, 2, 3 points that are the seed points. Then we need to specify the sampling length. This is the minimum size of leak that we want to detect. So it's advisable to have an idea of our gaps. In this case, we have something like 6-7 millimeters. This size has to be similar to the minimum element length of the wrapping that we will use, for example. It shouldn't be too small to find, too many holes and openings, just the ones that are important to be sealed. So in this case, I will specify 2. And we have a new option now in version 21 called Close Leaks. This means that ANSA will find the leaks and will also close them. So depending on the complexity and size of the model, as well as the minimum length of the leak tool, this computation is quite intensive, and on a big model it may take several minutes to complete. It's also recommended that you start with a large leak size so that you quickly find the big leaks and close them automatically, and then you can rerun the calculation with a smaller size to find even smaller leaks. Okay, the computation is completed. You can see that ANSA has created 3D curves and 3D points. Let me remove visibility of FE model mesh. And it indicates the locations where it has found a leak and where it has closed it. Okay, so I can deactivate visibility of curves and points and switch to PID mode, for example. Or I can even switch to part mode, so that you can see. Let me give a unique color to this part. So that we can only focus on the areas where we have patched the leaks. So you can see some closures here, there, gap closures there, and also here where we have a missing part. ANSA has closed this gap. It has also closed gaps here. Right. So if I deactivate the visibility of this part, you can see that and that. These are all the leak patches. And of course I can rerun the calculation so that it creates more leak closures with a smaller length. Okay, let's now switch to the new functionality that relates to cavity remeshing. This is a very powerful functionality because it allows the user to take an existing full mesh with surface and volume mesh make some small modifications of the geometry, and then automatically remesh only the volume that is affected by that change. This functionality can be achieved in two ways. I will show you the first one is through macros replace, and then the other function is volumes replace cavity. Okay. So this model is actually a complete volume mesh here. You can see a cut plane which is finite. I will switch this to not finite so that you can see that this is a full volume mesh. Right, I can move this in Y direction and see how the volume mesh is everywhere. Right, so I will switch to finite again so that we can focus on the area of interest. So in this example we would like to make a typical local geometry modification, that is to replace the side mirror with another design. The first way actually is quite straightforward. It doesn't require anything from the user apart from directly making the local modification on the surface, and we will do this through macros replace. I will deactivate the visibility of cut plane so that we don't have to see the volume mesh. Okay, and I will select replace. Replace, now I need to specify select the PIDs that I want to replace. So I will select the PIDs that form the side mirror. Confirm. And now ANSA asks me to select the file that contains the new design, right? So this is a different mirror. That was the original and this is the new one. I will press open and confirm here. And now ANSA will dig a cavity of the volume mesh, will erase the volume mesh in that area, will remove the old mirror, will bring the new mirror, will connect the surface mesh without losing the volume mesh, and will reapply the volume mesh after the modification. Right, so this is the top cap, this is the new surface mesh, and if I bring my cutting plane, you will see that the volume mesh has adjusted exactly, right? So I can also remove the finer plane, bring it back, right? So you can see this worked fully automatically. For this to work, of course, the volume mesh, that is the layers and the volume scenarios, need to exist in the ANSA file, because this is how ANSA knows how to remesh the volume. It knows exactly what layer strategy to reapply and what kind of volume mesh to fill in that gap. I would like also to show you the alternative way of performing remeshing cavities in volume. Instead of going through macros replace and directly replacing the surface mesh, you can go to volumes, replace, cavity, new, and here you need to select a morph box that contains the volume mesh that you want to erase. So I will select this volume, this morph box, and now ANSA will erase the volume mesh inside that box and will create this top cap, let's say, this skin of elements that will allow me to do any modification inside this space. So now I'm free to make any changes on my surface mesh, right? For example, I can switch to mixed mesh, right? Okay, so I made a change on the surface mesh. I can also replace geometry as well as before, right? There's no restriction to that. My cavity is always there, so I can make any change in that space. And after I'm happy with that, I go to replace and mesh. I need to select the cavity and press middle mouse. And ANSA will rerun again based on the volumes scenario for layers and volume mesh. We will execute again the volume meshing, and I will have a new volume mesh that of course has quads now in that area. Right, so two different ways to remesh volume cavities, either through macros replace or through volumes replace cavity. But remember, for this to work, you must ensure that you have generated the volume mesh using batch mesh, so that ANSA knows how to reapply it. For our next demonstration, we will switch to Morph menu, where we will show you the improvements in the function DFM. I will activate the function DFM. I will select geometry, I will select these macros, middle mouse, and I will specify a translation in the Z direction of 350 millimeters. Next, I can select another movement if I want to, or I can skip that. And now I will select the faces that will get deformed. So the wingtip will move as a rigid body, while this part of the wing will deform. And this will be the bounce. This area will be frozen. By default, you will notice that when this deformation is applied, there is some sort of discontinuity between the rigid body and the deformed. There may be cases where we want that, but there may be cases where we would like to have a continuous shape. In this case, we can go to the options list and switch from fast to accurate and tangency to smooth. And this will give us a nice smooth shape. Of course, you will notice that here we don't have continuity of tangency. If we want to have that as well, we can achieve it through the same operation. So this will move in the Z direction by 350, and then this middle mouse will move in the Z direction by 0, which means no movement at all. And this will get deformed. And we'll switch directly to accurate and smooth. And we will obtain continuity of tangency on both sides. Like that. Okay, now let's switch to a new function this time. Again, we have a similar geometry, a wing, and this time we want to deform it, but not as a rigid body, but we want to actually bend it. And we have a new function for this called bend. We select these macros, middle mouse, and you will see that ANSA creates a coordinate system and two opposite planes. And there are two handles that you can grab like that and interactively bend the wingtip. Like that. Let me undo. Let me show you also that while you are in the preview mode here, you can interactively move this coordinate system so that your bend is more local. What's even maybe more useful is that this also works with volume mesh. For this, we have created in advance a size box that will include the area that will be affected. We activate again the function bend, we select the same macros, and now we will also select the volume finder to be this size box, so that now ANSA knows that it has to deform also the volume mesh inside this size box. And you can now again interactively select and deform the wing like that, and the volume mesh will follow. Okay, for the next demonstration I would like to show you the function in CFD Decks Auxiliaries Rotating Interface. First of all, we have a new option called axis. In case you do not have the axis of rotation, you can select, for example, a PID. Take this wheel or that, middle mouse, and ANSA will automatically create a 3D curve that is the axis of rotation of your wheel, right? It passes through the center. This function is also included in the actual function that will create the rotating interface. Mind you, the purpose of this is to create an area that will separate the rotating region of the mesh with the stationary. So we'll create an isosurface a surface that offsets by a specific distance and includes the rotating wheel, the rotating disc brake, but will not include, of course, the brake caliper, which is stationary. So, activating the function rotating interface, the first step you need to specify is the axis of rotation. You can pick from the curve, or you can say again automatic. Then you need to specify what is the rotating part. So in this case, in PID, it's the wheel and the disc brake. The disc brake here, middle mouse. What is the static part? It's actually the brake caliper here. You can also impose areas where positions where there will be vertical intersection of the new surface. So I want, for example, the mesh to pass at that position, the surface to pass at that position, and to be also vertical, so that we can generate nice layers that will connect to it. So go to next and specify the offset, let's say 20 millimeters. Now ANSA will create a revolute surface that will offset from the selected rotating PIDs, but it will of course exclude the static PIDs, which are not rotating. And this will define the fluid zone that is rotating. Okay, here we are. This is what ANSA created. If we go to the part manager, these are the two surfaces that ANSA created. You will see that they are separate for the disc brake and the wheel. And if I bring the whole geometry and bring back the cutting plane, you will see that we have vertical intersection where we asked. We have an offset of approximately 20 millimeters from all rotating parts. And of course, in this area where we have the disc brake and the brake caliper, this rotating interface surface passes exactly in the middle, right? So that it allows for volume meshing on both sides. And ANSA has created, in this case, geometry, right? So these are actual faces that can be topologically connected. You can delete the inside part, which is in the dead region, and keep only the outside. And very quickly you have created a geometrical construction that actually took a lot of manual effort before. Okay, finally I would like to show you a functionality that is very useful to set up an OpenFOAM case in ANSA. This functionality is accessible through the user script functions here, and it's under Tools, Deck, Setup OpenFOAM Case. So this menu pops up, which is a customized menu, where you can select the OpenFOAM version you want, the solver, simple foam, the type of domain, inlet, outlet. You can specify what's the inlet, so question mark, and pick the inlet PID. What's the outlet? This one. You specify the turbulence model, K omega. Some parameters for the flow, turbulence intensity, and viscosity, number of iterations, how often to write results, how many time steps to keep. Let's say decompose this to 20 partitions. What is the mesh quality, so that we can specify suitable numeric settings. whether you have a wall function mesh or y+1 mesh, again to specify the appropriate boundary conditions. We want to monitor residuals, we want to monitor forces. Where do we want to monitor these forces? Again, question mark. Select, for example, the PIDs of the car. Specify the frontal area, reference length. You can also calculate mean values during the simulation so that you have an average flow field of pressure and velocity, also for turbulent quantities. You can specify pores and rotating zones. So here the fluid zone is not rotating, but the others are, and you can specify the origin, axis of rotation, and omega. You can set up the case. Oh, I forgot the velocity, 40 millimeters per second. And then ANSA will apply all the correct boundary conditions in every PID. Okay, so if you pick, for example, this PID, it will specify the correct boundary conditions for velocity, for K, omega, and so on. In addition to that, once you set up the case, we have the auto run case option, where we can generate automatically a script that will execute all the OpenFOAM steps, which is to decompose the mesh, to run potential foam, apply boundary layer to initialize a boundary layer on the walls, and run the solver, right? And you can specify an output directory. You can say create shell script, and ANSA will generate in that folder all the scripts that are needed to execute the OpenFOAM case, which is to decompose, to run potential foam, apply boundary layer, and simple foam. And this is very helpful because it fully automates the execution of the OpenFOAM steps. There's another script that will also monitor all the residuals and plot real-time the residuals, and you can also stop the solution at some point. And this concludes the ANSA demonstration.
In Meta version 21, the CFD Post toolbar has been redesigned so that it offers automation for the most frequently used CFD tasks, like multiple snapshot generation, as well as speed up during calculation of forces, force coefficients, also during the creation of plots versus distance, among others. So let's go and see how it works. First of all, the Template Manager button has been introduced, where the user is able to load the model. Let's select quickly a Fluent model to load. Okay. And after the geometry is loaded, we are able to read the results from this Template Manager window. We can read multiple results in one step. For example, in order to do that, we need to press the 3D Results button. And here, from this list, we can select the results that we want to load. By default, pressure is activated. By pressing the plus button, we can add the results that we want to load. Let's select velocity magnitude for now. And we can keep adding as many as we want. Okay, let's keep pressure and velocity for now. Also, let's go to the vectors list and select velocity vector result. Now I can press read and read the results, but there's also the option to save this list, the settings that I have made, and then load them back in the next meta session so that I won't have to do it again. Now let's press read. Okay, the results are read. Let's activate the fringe bar, and this is the velocity magnitude. Okay, let's have a look in our model, and let's switch the visualization of the results to on node and contour plot. Adjust the range a little bit. Okay, now the first tab of the CFD Post toolbar is called Snapshots, and what it does is to help us generate multiple snapshots along a cut plane, along the path of a cut plane, or multiple 3D views. Now, in order to create snapshots along the path of a cut plane, we need to select a pre-existing cut plane. So let's go and create one very quickly in the x-axis, and let's bring it back like so. Okay. And now, actually we have created the cut plane so that the toolbar uses it to visualize the result according to the settings of the cut plane. In order to generate the snapshots, first we need to select where the snapshots are going to be saved. So let's create a folder on the desktop, like so. And then in this list we can create snapshot generation tasks. We can do this by pressing the new button to create a new task. And now Meta asks to select the cut plane that we will be using for the snapshot generation, then the axis of movement of the cut plane. In our case, I will select X. And finally, Meta also asks to specify the start and end point of the cut plane. We can pick the start and end point using the pick button, like so, or we can press AutoCalc, and what it does, it actually calculates automatically the minimum and maximum X coordinate of the visible entities. Okay, then we specify the number of snapshots that we want to generate, and also from this list we can select the view that will be applied on the model in order to generate the snapshot. Let's select the front view. Any other user created views, custom views, are also loaded in this list. And we can also select the result that will be activated during the snapshot generation, and also the fringe bar minimum and maximum values. Let's select 0 for minimum, 50 for maximum, click OK. And we see here that the task has been created. We can continue and keep adding as many tasks as we want, using the same cut plane or another one if we want. We can create another task in the Y axis this time. Now, if I press AutoCalc, the minimum and maximum coordinates of the visible entities along the Y axis are calculated. Let's create 20 snapshots in the Y axis, and let's see the model from the side for this task. So I'm going to select the side view, the F3 view. Let's select velocity magnitude and minimum and maximum values, 0 to 50. There is also the ability to edit a created task. For example, if a mistake is made, I can select the task and press edit. And from here, you can see that I have selected pressure, for example, but the minimum and maximum values are not correct for pressure. These are actually correct for velocity magnitude. I'm going to correct this, press velocity magnitude, and press OK. Now I'm going to press new to create also an extra task in the Z-axis, auto-calculate minimum and maximum, specify 30 snapshots, for example. And now we would like to see the model from the top view, F1, velocity magnitude again. We can select any result that we have loaded. Okay. Minimum and maximum the same as previous. And now, in order to run the tasks, we need to select them because the selected ones will run, and then press the run button. We can also press the preview to see the cut plane moving and the snapshots that will be generated. I'm going to press run directly. And if we go to the desktop folder that we have created, we can see that it's being updated with a snapshot that are being generated as the cut plane moves. Okay. We also get here in the terminal window, in the info window of Meta, the snapshots that are being created. And finally, all tasks are completed. If we go to the desktop folder, we can see all the snapshots that were created, in the x-axis, also the side view in the y-axis, and finally the last task in the z-axis. So we can create as many tasks as we want using the new button. We can remove tasks, we can edit them, and finally press run. In that way we can automate the generation of thousands of snapshots according to our needs. Now let's see the second sub-tab of the Snapshots tab, which is called 3D Views. What it does is it actually helps us to generate 3D views, snapshots of our model according to our specifications. In order to do so, we need to organize our model in sets, because this tab actually gives us the ability to select which sets of the model will be active, will be visible during the snapshot creation, which ones will have results on them, which ones will be colored according to a custom color. So let's go and see how it works. First, let's create the sets that we're going to use. I'm going to create a new set from PIDs. For example, I'm going to put the mirror PIDs in a set called mirror. Okay, I'm going to pick them from the screen, like so, and our set is ready. Now I'm going to create an extra set for the rest of the car. Okay, and we can see that we have two sets, one for the mirror, one for the rest of the car. Now let's go and create some snapshots. We can do this again by pressing the new button. Again, we can select a separate folder, but I'm going to keep the same as the cut plane snapshot. Okay, and now press new. Now Meta asks to select which sets we want to keep visible. So I'm going to press pick and select the sets from the screen. Next, we define which sets will have results visualized on them. Again, using the pick button, I'm going to select the mirror. Next, I'm going to select the set that is going to have a custom color, the rest of the car, and here I am able to define this custom color. By default, a transparent gray is selected. Then I can select the results that will be used for the visualization of the results on the sets with fringe. For example, velocity again, from 0 to 50. And then we can select the views to be applied before the snapshot generation. From this list, we can select either one or two or multiple views. I select all of them to create 7 snapshots in total. And the task is created. Again, I can edit it, remove it, or I can create another one. I'm going to select the same set to be visible, and now I'm going to have the results on the car and the mirror colored in gray. Again, velocity magnitude, same range. Again, all the views, and I have the two tasks. I can preview them or press run directly, and we see that Meta will apply the settings that we have selected for the visualization of the model. And if I go to my folder, I can see the snapshots that were created. We can see that the mirror has results, the rest of the car is transparent gray, and the next task, the car is colored with results, and the mirror is transparent gray. So in that way we can automate the generation of snapshots all around the car according to our own views, and create as many as we want. Let's move on to the next tab, which is called Forces, and this helps us calculate aerodynamic forces of the model. First of all, I can press the read reference values from model, and now the free stream velocity, the reference density, the projected area, the frontal area are read directly from the solver. Or if this information is not there, I can type it manually. And then I can press the Calculate Forces button, select the PIDs that I want the calculation to be applied, For example, I can press select visible if only the car is visible, like in that case. Press OK, and we see that Meta reports the total forces in the x-axis. This is the drag force, the drag coefficient, and also the percentage, the contribution of each PID to the total drag. Okay, and finally we have the sum. Also the side force, the y-axis, and the side force coefficient, as well as the lift force in the z-axis, the lift coefficient, and the contribution. In this tab, we can see the total aerodynamic forces. We can also switch to this tab to see the pressure forces in all three axes, as well as the viscous forces in the third tab. Okay, and let's move on to the next tab, which is called plots. And what it does is it helps us generate plots, 2D plots of forces or force coefficients versus distance. In order to do so, we need to align the model so that we can see it from the side, or actually so that we can see the direction of the flow from the side. Now the flow is in the x direction and the model is aligned parallel to the screen. Then I need to select the option force coefficients versus distance or forces versus distance. Let's go for coefficients. Then define the number of steps. The more steps I add, the more accurate the display of the plots is going to be. Let's select 20 and press calculate. And now the calculation of plots takes place. And we'll see the results in a few seconds. And we can see the three forces that were generated in the x-axis, the y-axis, and the z-axis versus distance. Let's go back to our model and the CFD post toolbar. And finally, we have the last tab, which is named Tools. And this helps us do various things that are useful for the CFD user. For example, we can, if we go to the first sub-tab, Output Results, we can select a scalar result that is already loaded, like pressure or velocity magnitude, and then press Output to export it in CSV format. We can export the values for the shell results as well as the solid results. The next tab, Field Calculation, is available only for OpenFOAM models, because by default OpenFOAM doesn't write total pressure or pressure coefficient. The CFD Post toolbar gives this ability to generate total pressure or pressure coefficients from the available OpenFOAM results. And finally, we have the Create Report sub-tab, where we can select a folder that generates any number that contains any number of snapshots, like the one that we have used in this demonstration. And then, if I press Create, what it does is to create a report with as many slides as the number of snapshots included in the folder. We can see here that a report has been created. Each slide contains one snapshot from the folder, and I am able now to save the report in PowerPoint format or PDF format or any other that's supported. And I can also modify the presentation. I can add tables, images, text boxes, and any other element that is needed. Okay, and this concludes the demonstration of the CFD Post toolbar, which is available in Meta version 21. Thanks for watching.